On this video, we will discuss DeMoivre's theorem. So let's get started. Let's start by remembering that this is how we define complex numbers, at least in trig form. R cosine plus I sine theta. And our objective is to define z to the second, to the third, to the fourth, and to the fifth. So we know that this is how regular complex numbers are being defined. This is just a standard form. So what happens if we multiply this number by itself? Or in other words, what happens if we find z to the second? Well, z to the second, that's equivalent to z times z. And by the way that we have defined our z's, our first z, it's r cosine plus I sine. So this is the value of my first z. Now I want to multiply this by another z, which in other words, I'm going to just multiply by another r cosine plus I sine. So what happens when we multiply two complex numbers or the same complex number by itself? Well, according to our rules from our previous lesson, we know that the modulus are going to multiply. In other words, we're going to have r times r, which is just r to the second. And also remember that when we multiply, the arguments get added, but notice that we're using the same angle because we're multiplying by the same z. So in other words, we're going to add the same theta, which now theta plus theta, that's equivalent to just 2 theta plus I sine, and another theta plus the same theta, that's equivalent to just 2 theta. So notice that this is the result when we got z to the second. So z to the second, it's equivalent to r to the second times cosine of 2 theta plus I sine of 2 theta. So we have properly identified what z to the second is. Let's try to define, let me use a different color. Let's use green here. Let's try to define z to the third. So now z to the third, we can see it as being z to the second times z. But notice that z to the second, we already have an expression for that. Z to the second, that's equivalent to r to the second cosine of 2 theta plus I sine of 2 theta. So this is my z to the second, and now I gotta multiply this by another z, which remember that z, it's equivalent to r cosine I sine cosine plus I sine. So this is essentially what z to the third is going to be, but notice that we're multiplying one more time. And the rule implies that when you're multiplying, you gotta multiply the modules, which in this case is gonna be r to the second times r, well that's equivalent to just r to the third. And remember that we also said that when we're multiplying, we gotta add the arguments, where if we add the arguments here, we're gonna have 2 theta plus another theta, well that's equivalent to just cosine of 3 theta plus I sine of 3 theta plus another 2 theta plus another theta, that's 3 theta. So note that this is the result. So this is the result of z to the third. So what happens if we want to now define z to the fourth? Well, z to the fourth, we can see z to the fourth as z to the third times z. But notice that we know exactly what this is, because z to the third, we have already defined it here. Z to the third, that's r to the third, cosine of 3 theta plus I sine of 3 theta. And now let's multiply this by another z, which remember that z was being initially defined as r cosine plus I sine. So now we got r cosine plus I sine. And notice that we're multiplying, so the rule of multiplication says, well, when it comes to my modulus, I'm going to multiply them. So r to the third times the same r, that's r to the fourth. And when it comes to my arguments, we're going to add them up. So 3 theta plus another theta, that's 4 theta, plus I sine 3 theta plus another theta, that's 4 theta. So now notice that this is r z to the fourth. But notice that if we keep doing this, You keep doing this, you might have already started guessing that, well, perhaps z to the fifth, z to the fifth, it might be r to the fifth cosine phi theta plus I sine phi theta. And you can see that z to the 6, I mean, we can keep multiplying this and you will see that z to the 6, that's r to the 6 cosine 6 theta. And z to the 7, that would be r to the 7 cosine of 7 theta. And notice that all we have done, we have just used the rule of multiplication when it comes to complex numbers. And now we want to be generalized in this form. Because notice that when we're multiplying to z to the second, it was the r to the exponent of the number that we want to multiply at. And cosine was 2 times the exponent that we had here. Z to the third, that's r to the exponent, which is to the third. And cosine, the exponent theta, which in this case is 3 theta, because we wanted to raise it to the third exponent. To the fourth, r to the fourth, cosine 4 theta. To the fifth, r to the fifth, cosine 5 theta. And the general form that we have for this observation is what we refer to as the DeMoivre's theorem, where the DeMoivre's theorem says that for any complex number, which we can define as r cosine plus I sine, then when we raise that same number to some exponent, then the result is going to be r to the n cosine n theta plus I sine of n theta. And notice that this follows the idea that we had in this small introduction problem, because all we're doing, we're multiplying the same z value by itself, and we're just using the rules of multiplication that we defined previously. So let's actually apply this. In a problem. Well, another way, before we apply this on this following problem, notice that z to the n can also be seen as just r cosine plus I sine all to the n. And when we have it in this form, then that's equivalent of just writing it out as just the exponent equals to the r n theta plus I sine of n theta. And this is just the same format or the same conclusion that I stated previously. But now, how or why is the DeMoivre's theorem so useful? Well, because now let's take a look at this example right here. We want to multiply this complex number by itself 12 times. So if we don't know the DeMoivre's theorem, then you might be tempted to just say, well, you know what, I'm just going to do it the long way. I'm just going to get this complex number and just want to multiply by itself 12 times. I mean, you can definitely do this. You're going to have distribution, and then this result, you're going to have to multiply by this one more time. And then this big expression, you're going to multiply one more time. Then a bigger expression, you're going to multiply one more time until you do that 12 times. So that's one way of finding this complex number raised to the 12. But we definitely have what we call the DeMoivre's theorem now. But we can definitely use the DeMoivre's theorem here. But there's this small problem with the way that this problem is stated. In order for us to use the DeMoivre's theorem, notice that my complex number needs to be written in trig form. So that if we want to use the DeMoivre's theorem, the first thing I want to do is get our complex number and try to define it in complex form, in trigonometric form. So let's start by doing that. In order for us to write the number in trigonometric form, we got to find the value of r, which recall that r is the real square, which is 1 square, plus the imaginary square, which is square root of 3. So now we know that r is equivalent to 1 plus square. So 1 square is 1, square root of 3 to the second, that's 3. So now r is the square root of 4, so now we know that r is equivalent to 2. And now remember that in order for us to find the argument, it's always the inverse of tangent b over a, or the imaginary over the reals. So the tangent, that's equivalent to -1, square root of 3 over 1. Now we're taking a look at our unit circle, and what degree in our unit circle do we have such that if I value it by tangent, it gives me a value of square root of 3? Well, for that, that will be pi over 3. So now we know that my angle is pi over 3. Do we have to do anything to this? Well, recall that this is, if we take a look at where this point is located, this point is on real is positive, imaginary is positive. So it is on this point is on the first quadrant. So therefore, my angle of reference is the same as the argument. So we're okay with that. So now that we have this, we know that the value of r and the value of theta, now we know that perhaps we can rewrite this problem in its trig form, where the trig form is going to be equivalent to just 2 cosine pi over 3 plus I sine pi over 3. So this is how our complex number looks like if we want to write it in trig form. So now that we have it in trig form, we can definitely use DeMoivre's theorem. Because now, DeMoivre's theorem says is the following. This big number, 1 plus 3i to the 12, this is equivalent to just 2 times cosine pi over 3 plus I sine pi over 3 to the 12. And now the DeMoivre's theorem says that if you have any complex number raised to some exponent, well, this is equivalent to just 2 to the 12 times, or a big multiplication, times cosine of 12 times 0.3 plus I sine 12 times 0.3. Because this is essentially what we just discovered here. If we want to raise it to the second, then r is to the second, and the angle inside the cosine, it was 2 times the given angle. If it was to the third, then r was raised to the third, and inside the cosine, it was 3 times the angle. If it's to the fourth, then r to the fourth, and inside the angle is 4 times the angle. Well, in this case, since we want to raise it to the 12, then it will be 2 to the 12, and inside the cosine and the sine, it will be 12 times the angle. And remember that the our angle, we define it here as pi over 3. And now this is just a matter of just finding this on your graphing calculator. Where 2 to the 12, that's equivalent to 4,096. And now inside the cosine, well, 12 divided by 3, that's just 4. So now this becomes 4 pi plus I sine 12 over 3, that's 4 pi. And now essentially, this is our result. This complex number raised to the 12, it's equivalent to this expression right here. But notice that we can simplify this, because we can definitely evaluate what cosine of 4 pi is and what the sine of 4 pi is. Because now this just becomes 4096. And the cosine of 4 pi, well, where is 4 pi? I know that if I make one circle, that's 2 pi. If I make another circle, that's essentially 4 pi, where on 4 pi I have 1 comma 0. So the cosine, it's equivalent to 1 plus I times the sine of 4 pi is 0. And now this just becomes 4096 times 1, because 1 plus 0 imaginary is just 1. So this is just equivalent to the value of 4096. So what we have shown, and again, you can double check this, which I'm not going to do it in this video. What we have shown is that if you were to multiply the same expression if you were to multiply the same expression 12 times, if you would have done multiplication, 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 and you spend a good time on it, you're going to end up with this value if you do it correctly, 4,096. And notice that this is just an easier way to multiply complex numbers as long as you have them in some kind of a exponential form. This is just a shortcut. This is just an easier way to get to the conclusion. Hopefully this was helpful with the DeMoivre's theorem.